Hello, my name is Rusty Bascom. I am a principal engineer with Electrical Consulting Engineers located in the United States. Today I'm going to share with you a summary of our paper entitled The Life Cycle Experiences for 115 kV Underground Pipe Type Transmission Circuit Cooling System, which describes some strategies used by a U.S. utility to both extend the life of the cable system and to achieve some additional cable rating capacity during the life of the system. It also describes the end-of-life criteria for some of these enhancements and how the utility intends to use the system going forward. The co-authors for the paper include Mohammed Pasha from United Illuminating Company and Tom Zhao from the Electric Power Research Institute. I am including my email address as part of the presentation, and in the event you want to ask any questions, please feel free to email me at the conclusion of the presentation. The cable system life cycle is usually evaluated during the planning stages for a new project. In the case of this particular project, the utility was doing planning and engineering design in the late 1950s, and the cable system was put into service in 1961. The end of life for a cable system occurs when either it can no longer operate or it is unable to meet the energy delivery requirements for the utility. In the late 1990s, the utility forecast that the energy delivery available from this circuit was not going to meet the capacity needed, and so they studied ways to improve the capacity on the cable system. The capacity on the cable system was improved by implementing two technologies. First, a parallel pipe forced air cooling system was installed in 2002, and real-time thermal ratings were implemented on the cable system in 2004. Both of these elements are no longer needed, and so essentially have reached the end of their life, which is the subject of this paper. The cable system consists of two 115 kV pipe-type cables installed in a common trench, located in Connecticut in the United States. Most of the route was constructed using open-cut trenching methods, with the two pipes running in parallel. One segment of the route crosses underneath a harbor. For this segment, there are actually three pipes installed, two containing power cables, and a third is empty. The empty pipe was intended to be a spare because of the limited access available to make a repair on the energized cable pipes in the event one of them was damaged or suffered corrosion. The idea was that the cables could be pulled into the empty pipe rather than trying to make a repair to one of the energized cable pipes. For the purposes of upgrading the capacity on this circuit, the empty pipe was ultimately used as a cooling pipe to cool the two energized cables and increase the capacity on the circuit. The pipes are installed at a depth of 3 to 8 meters below the water bottom across the harbor, and the pipes are separated from one another by 0.7 meters, as shown in the diagram. As discussed earlier, the initial design life of the cable system was 40 years. Rating studies were done in the 1980s and again in the 1990s, where the peak rating was actually decreased because the loading pattern had changed. Essentially, the load factor had increased, meaning that the allowable peak current had to decrease. A study done in the early 2000s identified the harbor section as the limiting section for the cable circuit, as shown in the diagram. Real-time ratings were implemented to improve the ratings, as well as parallel pipe forced air cooling to mitigate the limiting section across the harbor. During some of the studies that were performed on the cable system, an evaluation was done on the historical loading patterns to evaluate the daily load and loss factors, which did have an impact on the rating. Also, historical loading was studied to evaluate the typical loading patterns and the resulting temperatures that were experienced by the cable system over the life of the cable system. And those were evaluated in combination with an Arrhenius relationship to assess the insulation aging that may have occurred during the previous 40 years of the cable system's life. At the same time, there was some new planned underground transmission, both at 115 kV and 345 kV, that would serve the same general vicinity as these 40-year-old circuits. By increasing the capacity on these circuits, they could continue to operate and meet the utility's needs while the new transmission was being constructed. The needed capacity on the circuits was an increase of 2 to 3% in the underwater section, and it was for this reason that real-time thermal ratings and also the parallel pipe air-cooled system was implemented to achieve these additional capacity goals. The parallel air cooling system was initially developed as a research project and then commercially constructed to provide a permanent means of cooling the spare pipe and the adjacent energized cable pipes. This slide illustrates elements of the air cooling system that was used to increase the capacity on the cable circuits. The photos on the top left show the blower assembly that was temporarily installed on the spare pipe to evaluate the cooling capacity of the empty spare pipe on the two adjacent energized cable pipes. The photo on the bottom left is the commercial air handling system that was permanently installed to provide this cooling function. The graphs on the right illustrate the models that were developed to evaluate the cooling capacity on the cable circuits. The top graph shows the temperatures within the empty pipe without any air cooling, and the graph on the bottom right shows the air temperatures with the air circulating through the empty pipe. These temperatures were verified using thermocouples installed in the empty pipe, as well as a distributed temperature sensing fiber that allowed for measurement of the temperatures along the length of the pipe in order to characterize how effective the cooling was occurring on the cable system. After the new underground 115 kV and 345 kV crosslink polyethylene circuits were commissioned in 2008, the added capacity from the forced air handling system was unnecessary. The real-time rating system was also not needed because the additional 115 kV and 345 kV circuits provided redundancy and additional capacity to the area. In 2019, the utility planned to relocate the substation nearest to where the air handling system was located. And as a result of this relocation, the air handling system can no longer be connected to the spare pipe. As a result, the air handling system and the real-time rating system are being removed. The nearly 60-year-old underground pipe-type cable circuits will remain in service because they offer an enhanced reliability and redundancy to the existing transmission system. In conclusion, the utility was able to extend the life of an over 40-year-old cable system by applying available technologies. Ultimately, the end-of-life criteria was met for these subsystems, and they were removed from service. But the cable systems themselves will continue to operate for many years more. Thank you for listening. As I mentioned earlier, if you have any questions about the presentation or the paper, please feel free to reach out to me by email.